Okay, so in this lesson, we're going to focus specifically on the line segment, the tangent, the line that's tangent to the circle. So before we get too far, let's review what some of these vocab words are. So starting with the arc, we know the arc is part of the rim, the outer part of the circle. We know that a chord is the segment that goes inside the circle, and then we call it a secant. If it keeps going and goes outside the circle like that, then we would call it a secant. But just the part inside the circle we call a chord. Then what we haven't talked about a lot, I've kind of mentioned it, is a tangent line. This is a line that intersects, technically. So we might think of the word intersects as in like touches the circle in exactly one point. So this right here, friends, is a tangent line because it touches the circle in exactly one point. It doesn't touch the circle and it doesn't go all the way through and touch it in two places. It just touches and then goes on and does its thing. The point where it touches the circle is called a point of tangency. Which makes sense, right? Keep in mind a tangent doesn't have to be a line. It can also be a segment or it can be a ray. So you could have that's still tangent even though it stops. It doesn't keep going on and on forever. This is still a tangent even though it's a ray. So don't let that throw you off. So in this Geometry Sketchpad investigation, let's take a look. I've started it for us already to save a little bit of time. What I have here is a lovely circle, and I have a secant line right now. So I can move this point all the way around the circle. When I move it on top of this other red dot, then it becomes a tangent line, right? Then it's only touching the circle at one place, but anywhere else around the circle, it's intersecting at two places. The other thing I need to create here is a radius. So I'm going to go from the center out to the rim of the circle. I'm going to have it touch right here to that one intersection point. Okay, so nothing magical happening there, right? And then the other thing that we want to do is we want to look at the degrees of this angle here. So I'm going to measure that angle, and it's going to be called angle ABC. Okay, so as I go around the circle with point A, notice what happens to that angle. It's getting bigger, it's getting bigger. I hope you're watching this number right here, right? Getting bigger, 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 bigger. Oh, now it's getting smaller again. The farther away I get from point B, the smaller it gets until I get all the way to the diameter, and then it starts getting larger again. What happens when it gets exactly on top of point B, I wonder? It's really, really close to 90 degrees, isn't it? I wonder if that would still be true if I move point B. What if I do... It's still almost 90 degrees. It seems like any time that I make that line, not just a tangent line, but I make it not just a secant line, but I make it a tangent line, that angle becomes 90 degrees. The tangent line is perpendicular to the radius. That forms a 90-degree angle. And friends, that is our first theorem for today, is that if a line is tangent to the circle, the only way that can happen is if it's perpendicular to the radius drawn at the point of tangency. Then the line is perpendicular. So this is always going to happen. Tangent lines, so here's my tangent just to give you the full visual. Tangent lines are always going to form a 90-degree angle with the radius. Okay, so let's look at example number 1. It says assume that the lines that appear to be tangent really are only touching the circle in one place. They really are tangent. And C is the center of the circle. Find the value of x. So let's take a look here. I'm noticing I've got 58 degrees as a central angle. I've got x over here as this angle. And now what I know, according to my new theorem, is that the tangent and the radius form a 90-degree angle. So now I have a lovely right triangle. And so if I want to find x, 180 minus 90 minus 58 gives me 32 degrees for x. Okay, so you try, pause the video. Notice this one is not a triangle. This one you've got some kind of kite-like shape. But the key to this problem is thinking about how the radius and the tangent line form a 90-degree angle. Okay, so on this one, I have 2 radii and 2 tangent lines. So I've got a 90-degree angle there, and I have a 90-degree angle over there on the left. A couple of different strategies you could use to work this problem. Because it is a kite, if you wanted to, you could split it down the middle and split it into 2 separate triangles. I'm going to go a little bit faster route. I remember the fact that all the angles in any quadrilateral, this yellow 4-sided shape, add up to 360 degrees. If you didn't remember that, that comes from that n minus 2 times 180. 4 minus 2 times 180 would be 360. Minus 90, minus 90, minus the 130 up top. I'm just subtracting all the angles except for x. And we get 50 degrees for x. Now, again, that's not the only way. You could have divided this up. If you're going to do that, you would split the 130 into 65 and 65, in which case you would do 180 minus the 90 over here in this green triangle minus the 65. That would have left you with 25 for half of x, and then you would have had to have known that this side was also 25. This angle is bisected, in which case x, the whole thing, would be 50 degrees.